writing down qubit states. So my expectations here are that I hope this is not going to be too down in terms of really technical mathematical level of writing a qubit, but maybe because I really like the visual way that Hello Quantum gives you to understand to understand a qubit and how a qubit is shaped. But I see already in the table of contents that we're going to talk that this guy talks about the x basis, the y basis, and the z basis, the x basis, and the y basis, which I think it's good. So those are sort of the three dimensions that I talked about. And yeah, let's see what this is about. Let me just get the color in here. So in the previous chapter, we saw the multiple ways to extract an output from a qubit. The z basis. Let's just go through it directly. Do it directly. If you do nothing in a circuit but a measurement, you are certain to get outcome 0. Yeah. Okay, so here's just talking you through the basics of how do you name states. So we're going to name this 0 and this 1 with this fancy notation. Mathematically, those are vectors. And there's a lot of notation to take. Again, this is the Dirac. I think it's pronounced Dirac notation. And basically vertical vectors are represented like that and horizontal vectors like that. So this is a Brian, this is a Ket, and they all together are called bracket. It's just, I find it funny, but I think that's not everything entirely needed. If you're not planning to really go down into sort of like proving certain things or like writing down circuits in terms of mathematical expressions and then figuring out what's the final state, etc. I think that's I have a video on sort of a more intuition-based type of calculation you can quickly do on a notepad to kind of try to understand a circuit. So, but if you want to know the details, because those are basics about multiplying matrices, and blah 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 blah. Good. Okay, so the x basis. So far we looked into states with the z measurement. Good place to start would be okay. So, but there are also states for which the outcome of a z measurement is equally likely to be 0 or 1. How do those vectors look like? Okay, so it goes to mathematically saying 0 or 1. Okay, and we can get any value of the inner product that we want. This condition is normalization condition. Yeah, I mean, it's for sure interesting and useful, but I don't think that we need to go through that intuitively. We've got 3 states we can write. Okay. Oh, I mean, here I see the plus state. Okay, so here's defining that as the plus state. Yeah, it's kind of basically saying it's. So the basic here is. Yeah, maybe I should go through all of it in detail, but the basics here are that this is a condition and condition. Okay, so let's choose for the inner product to give the value 1. So they don't really. So in plain English, I would say the when you express the vectors, when you express the states as vectors this way, in terms of exactly like here you have like an x and then this and this. Okay, so the 0 and 1s here, right? So if you have a state in which you if you square the modulus, if that's called this way, of whatever factor you have in front of, that should always be 1. But I think that's going to be explained later. I'm tricking myself right now because I know a bit of this, and it just confuses me the way this is being introduced. But but here we are defining a state plus, which is basically that. And then what is the Born rule? We've got three states that we can write down as vectors. We can also calculate in the products. Probabilities. Represents a generic qubit state. All probabilities in quantum mechanics can be expressed this way. It's a bunch of, for me, it's a bit confusing to go through all that mathematical notation. Even though I get it, it's probably needed if you want to really global and relative phase. So vectors, I'm going to go through this kind of my way and then see if I can abstract the learnings out of that at intuitive levels. So vectors are how we use math to represent the state of a qubit. We use them to calculate the probabilities of all the possible things that could ever be measured. Let's find an example. Consider the state that looks like that. This is equivalent to multiplying state 0 by minus 1. And as you probably know, the negative number squares to the same value. So this means that we could ever... Okay, so this means that technically there's no difference between that and the zero state, right? But it is not true if the phase is relative rather than global. Relative rather than global. This would mean this is known as the irrelevance of the global phase. Quite simply, this means that multiplying the whole of a quantum... Okay, this is probably the important bit here. So multiplying an entire state by minus 1 gives us a state that will look different mathematically, but it's physically the same, right? Because the probabilities of observing the different results are the same. Okay, so basically, and that's why they say the relative phase, it's important. Phase is like, I don't know, they just dropped that here, right? As if like, hey, let's call that a phase. That comes from the physical language, I think, of quantum computing. I intuitively translate that into, the plus or the minus signs. Same is not true if the phase is relative. This would mean multiplying only part of the state by minus 1. So if you do that on the plus state, you get a minus state, and then that's defined like the minus state. Okay. The X basis part 2. Whenever we find a pair of orthogonal qubit states, we can use a new measurement. First, let's apply this to the case we all know, the Z measurement, 0 and 1, okay, and then plus and minus. Yeah, those make the other bases. So I'm not so sure. I'm guessing that is probably not a super helpful review of that part of the tutorial. I just find it a confusing way to introduce those concepts. Conservation of certainty. We can make the explore of the states, try this out yourself. You'll find examples where the Z measurement gives a certain result, but the X is completely random. You'll find examples where the opposite is true. Furthermore, there are many examples where both are partially random. With enough experimentation, you might even uncover the rule that underlies this behavior. That's what I was trying to get at. So basically, if you square up all the constants multiplying the states, that kind of should give you 1, because it means that all the probabilities, they will all add up to 1. The Y basis part 1. Okay. So here they're defining the Y basis with this funny circle sign. So that's how you define the other dimension. Complex numbers. Hopefully you've come across complex numbers before. Yes. A quick reminder. So, counting bananas. That's a funny thing. Counting bananas, you use real numbers for that. but there's no real number that starts the square root of -1. So here's where you made up the complex numbers, which is essentially the complex numbers are a tool to kind of lift up your counting space into another dimension without going full vector, right? Without saying, no, now we're going to count on using vectors. So you stay at the one dimension notation, but you're adding an imaginary number. So so then you have two components here. Okay, yeah, sure. That's all the basics here. Basically what it's saying is that if we're going to allow the numbers, the thing is, what this is trying to do is, I think what this part of the tutorial is trying to do is trying to kind of lay the foundations of how are we defining qubits mathematically. And while I think that's helpful, maybe it's not super needed in order to build up intuition on quantum computing, on quantum programming especially. And that's it. And that's it. Okay. Let me check. Conservation. So what have we? I mean, it's in general a bit confusing. Um, it's a bit confusing. It's just a mathematical foundation. I think that's, while interesting, it's probably um, not super needed to go through that. Okay.